There are two propositions associated with the Carnot cycle. The first proposition of the Carnot cycle is that the efficiency of an irreversible cycle must be less than that of a reversible cycle. That is, eta sub IRR has to be less than eta sub REV. And this makes sense. Any irreversibilities associated with the cycle, whether it's friction or unrestrained expansion of a gas, is going to diminish, say, the available work or require more heat input for the system to achieve, say, the same power output. So we'd surmise that an irreversible cycle should have less efficiency than a reversible cycle. We can try to disprove the first proposition by assuming an irreversible heat engine, HE sub IRR, operating between TH and TL, has a greater efficiency than a reversible heat engine, HE sub REV, that is operating between the same two temperature reservoirs. In the schematic below, we have our high temperature reservoir, denoted by TH, our low temperature reservoir, denoted by T sub L, our irreversible heat engine, denoted by HE sub IRR, the block on the left, and our reversible heat engine, HE sub REV, as a block on our right. Now note, a reversible heat engine can operate both as a heat engine or a refrigerator. Now, the work of our irreversible heat engine, W sub IRR, is equal to the difference of our heat input and heat output. That is, W sub IRR is equal to QH minus QL prime. Our reversible heat engine, being operated as a refrigerator, requires a work input based upon the quantity QH minus QL. We see the work of our irreversible heat engine is going to provide power to our reversible heat engine. Now, since QL prime is less than Q sub L, and the quantities of QH are the same, and since that our efficiency of our irreversible heat engine is greater than that of a reversible, that the work of our irreversible heat engine has to be greater than that of a reversible heat engine. That is, W sub IRR is greater than WREV, which means we have a surplus of power, i.e. W net. Our net work is the difference of our irreversible heat engine's work less that of a reversible heat engine's work. That is, we would have W sub IRR minus WREV being equal to W net. Since QH is the same, in this expression, we'd have minus QL prime plus QL, or rearranging QL minus QL prime. We see that our net work is only a function of our QLs, i.e. that this system is operating between a single temperature reservoir. This violates the Kelvin-Planck statement, which then invalidates our assumption that the efficiency of an irreversible heat engine is greater than the efficiency of a reversible heat engine. Thus, the first proposition is shown to be true. The second proposition of the Carnot cycle is that if any two reversible heat engines are operated between the same temperature reservoirs, they must have the same efficiency. That is, if we have a reversible heat engine 1 that operates between TH and TL, and then we place a reversible heat engine 2 that operates between TH and TL, they will have the same efficiency. If our second reversible heat engine is being operated as a refrigerator, the power supplied by our first heat engine is enough to power the refrigerator.